I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hey Ben.
Hey Matt.
How you doing?
Good.
So I've been thinking recently, there's an awful lot of cool things that processors do that I don't think people are aware of. Except when maybe they come along and ruin their day because they hear things in the press like Spectre or Meltdown or other side channel attacks, these scary sounding things that probably aren't quite as scary as you think. But there's a lot of technology and a lot of very cool and clever development that's gone into CPUs. And we have a podcast and I love talking about this stuff. So I figured, let's just write down Matt talks about CPUs and then see what comes from that.
There's a whole bunch of things that CPUs do that I don't know about. So I feel like I'm going to learn a lot in this podcast.
So I, many years ago, actually, I had a lightning talk, which was something like 5 things you didn't realize that your CPU does for you. And it was a fun one to do because it was for an audience of people that weren't necessarily low-level engineers, as indeed I'm sure many of our listeners are not necessarily interested in all the low-level things. Oh, both listeners. Sorry, there are 2. Yes.
Yeah, we have at least 2.
Exactly. I tried to come up with this format that was, I thought, interesting because they were only 5 minutes long anyway, but just phrasing it in terms of your CPU, even if you have only the vaguest understanding of like assembly code, machine code, or whatever's actually going on from the point at which you're typing your code to the point at which something useful happens in your computer, you've probably got this idea of, instructions that move registers around, like MOV EAX, 123, that kind of thing. Or if you're on ARM, something similar, or, you've maybe done some, RISC thing at university when you've been forced to take some kind of assembly course, and you kind of have a rough idea about the operations that a CPU can perform.
I think, okay, there's an opcode identified by probably an integer for each of these instructions, and they take some number of arguments, not totally unlike a function call, but they take some number of arguments.
It's a great way of thinking of it.
And they are things like, move this data from memory into this register. Take this register and add them together and put the result in this register. And that's sort of my, very basic mental model of how assembly works. And all of the basic operations of the CPU are represented by those commands.
So yeah, I think that's a really useful way of thinking about the way the computer works. You mentioned, like the arguments are like the parameters to the instruction as if it's like a function call. And I think the only thing I add to that when I kind of mentally model it is like the registers are global variables, right? At the end of the day, the CPU only has global variables, which is pretty horrible and pretty nasty. But so that one of those 5 things that I was talking about that you didn't know your CPU does is that your CPU is kind of a JIT compiler. It doesn't run that either. It only has the illusion, right? The instruction set architecture, the ISA, the machine code that you're giving to it, is an API boundary. And provided the CPU appears to do what you would expect it to do when you do MOV EAX, 1234, it is up to the CPU how it achieves that goal, right? It's a completely, it's an abstraction layer, right? What goes on underneath is completely up to the CPU. Now, you might reasonably think, like I do, because my mental model is sort of sat back in the 1970s, 1980s of CPUs, is that like there is a little box that says EAX somewhere inside the PC. And when I do MOV EAX, 123, then the number 123 goes into that box, right? That's what happens, right? But that's not what's happening at all anymore, unfortunately. Things have gotten far more complicated. And like the first thing that a modern CPU will do is it will take that expression, effectively, that you give it, this instruction, and it will devolve it into smaller instructions called micro-operations. And those micro-operations are what the actual core inside is going to work on. Now, in the case of that MOV instruction we were just talking about, it probably doesn't have anything more to do than that operation. It's like the operation is about as small as you're going to get. But when you're doing something like move from memory, there are several things that need to happen. And while we're here, let's just talk about a pet peeve of mine. Why on earth is it move? It's always move, and it's MOV this, that. There's no moving. It's not like the old value has gone away. It's copy, right? When I say move the value 123 into EAX, then I haven't actually just deleted the value 123 from outside of the world, right? There's no longer, it's a copy. It's like move, move. I can't even think of the right word without saying the word move. But anyway, but if you're say acting on memory and say the Intel instructions give you an awful lot of flexibility to say, do an add instruction where one of the operands is a register and the other operand is some complicated expression that says, read from this memory address offset by this other register multiplied by 4, because you're going to use it to index into like integers, and each integer is 4 long. There's kind of 3 things going on there. One is the actual addition. Another one is the calculation of which memory address was it that you actually wanted to go and read from. And I'm not talking about virtual memory here. I'm literally talking about the instruction was ESI plus 100 plus EDI times 4. And you're like, well, that's a complicated thing. And then third of all, there's the actual going to fetch the memory that is at that address. And so those really are split into 3 operations. And it's not just to make it simpler on the architecture underneath. The cool thing that's happening is that those micro operations can be broken apart and then executed separately and individually, which means that if, for example, the memory unit is free, but the adding unit is busy doing something else, then you can go off and fetch the memory or the memory calculation, go and fetch that, and then sort of hold on to that temporary result. And then when the adder becomes free, you can just do the add. You don't have to wait for all 3 units to be ready together so that you can do the operation.
Interesting. So is this like an extension of Moore's Law running out, where it's like they couldn't make processor any faster, so they just started giving us more cores? Now they're like, well, what if we take the operations and we do those in parallel too? Is that just
it
all
is exactly
is?
that? Yeah, except the sequence
is
is the other way around, really. You know, as Moore's Law was sort of reaching the end, and as we sort of hit the sort of 4 gigahertz-ish wall, instead of making CPUs more and more and more fast in terms of clock speed, the cunningness went along multiple dimensions. And parallelism is something that Silicon does. Like, it's hard to stop it from doing the parallelism. In fact, all of like chip design is trying to get rid of it from being parallel where you don't want it to be, and handling the crazy race conditions. I mean, I've never done silicon, but in terms of like FPGA design stuff, it's always the timing, it's always the synchronization points. And if you think you've got problems when you've got like multiple threads accessing stuff, try imagining you've got 2 million individual gates that are all doing their own thing. So the sort of the first axis, I mean, so back in the day, we're going to go back to like 6502 era, then it took multiple CPU cycles, multiple clock cycles to execute a single CPU instruction. So, you know, the classic fetch the instruction, decode the instruction, execute the instruction, usually, and then sometimes they have a retire stage or a write back stage and a retire or something like that. Those are kind of like the pipeline stages that an instruction went through, and he went through them one at a time, which was cool, but the obvious observation is it's a pipeline. The fetch you can be fetching instructions one cycle at a time, and then you can be decoding the next one and executing the one after. The other way around, you know, the classic pipeline, which is fantastic. And it meant that a lot of things that were taking 5 cycles to complete, if you imagine a 5-cycle pipeline, well, for every individual instruction, it does indeed take 5 cycles to get from one end of the pipeline out the other. But every single clock of the tick of the clock, you're doing one more piece of useful work, just like, a modern car production line. It might take 2 weeks for a car to be assembled from a bag of parts that are put in one end and come out the other for any one car. So if you were to like spray paint that car red, and then it would have to wait 5 weeks. But every day, a whole new car rolls off the end of the production line. And so you've got this latency throughput trade-off that's going on. And so we were already taking steps in that direction, even like, so I said the 6502 grabs these things. Actually, as it happens, the 6502 had a very, very simple pipeline where on the end of the last tick of an instruction, it actually was fetching the next instruction, which had some interesting, if you're ever going to emulate it had some interesting side effects, but we've done that to death. So there you're getting sort of parallelization out of a single stream of instructions, which is great. What tends to happen, though, in those cases is that only works if you know what you're going to be doing ahead of time. So in the case of the analogy we had with the car production line, it's like when you finally get to assembling the last step, you look at that part of the instructions and it says, oh no, make this one red. And you're like, oh, but it's already been all the way through and we're nearly at the end. The analogy I'm trying to make there is that's like a branch that's taken or not taken. You've made a decision and it takes a few cycles for the decision-making process to come to its conclusion and say, actually, we need to be doing something different here. But the pipeline is full of the other instructions that would have happened if you had just carried on in a straight line. So at that point, what used to happen would you'd have bubbles in the pipeline. So those fetched and decoded instructions that weren't going to be executed were just flushed away, thrown away, and then the whole thing would start again. And so it would take several clock cycles before useful work could be done again. And that's what made branches expensive back in the day. And that's cool. So what next happened was the concept of making a guess. Hey, if we can make a guess at where the branch is going to go ahead of time, then we can steer that that fetcher and a decoder in a particular direction. And then as long as when we get to do the execute stage, we check our guess. If we were right, hey, no harm, no foul, we carry on. Like the instructions that we've fetched and decoded are ready to go. And we don't have to have this bubble in the pipeline. And if we get it wrong, it's no worse than how we were before. We have to throw away the pipeline and flush it.
Yep. Now,
as it happened about the time that the branch predictors were coming in and becoming more and more important, it was actually the case that the pipelines were getting longer and longer and longer. For boring technical reasons to do with actually speeding up the clock speeds overall. Obviously, if you're making something go faster and faster and faster, it's better to have smaller and smaller pieces of work to do, which in this pipeline analogy means having simpler and simpler steps in the pipeline, but potentially more of them to achieve the ultimate goal. So now we're looking at latencies of the orders of tens of cycles between the fetch that picked up the instruction and the branch instruction actually running and determining, yes, we are going to take the branch, or no, we're not going to take the branch. So the interesting side effect of having a branch predictor, and we can talk to death about how they work, and they are amazingly, amazingly good these days, is that what the core, the sort of like the engine that's churning out all of the actual work, the stream of micro operations, remember we've turned these instructions into micro operations, it's just given a sequence with no branches in it, effectively, of instructions of work to do. And it can be filling that could be a huge amount of work. It can be hundreds ahead of itself, potentially, with a long enough pipeline. But also, what that gives it an opportunity to do is to sort of do, and this is where I'm going to go back to the analogy I made of like a JIT compiler. It's sort of just-in-time compilation. It can do some analysis of the stream of instructions, and it can say, this particular instruction that's later in the stream doesn't depend on an earlier instruction. So,
and this is all happening in the silicon?
This is happening.
This is in the hardware.
Completely in hardware. Absolutely.
Wow.
And so effectively, a DAG is being generated of all the interdependencies between instructions. And instead of running the instructions strictly in the order that you wrote them down, it is running these micro operations when they are ready to be run. So in the case of, say, a divide is a classical example of a really lengthy instruction. So I'm dividing two numbers together. It's going to take a good 12 to 24 cycles before I get the integer result of that divide. Meanwhile, the next instruction was just like, mov EAX, 12, because I'm setting up to do some other piece of work, right? Well, that instruction can run. It can jump the queue because there's no observable side effects that the divide needs. And so there's all...
It's not like it's moving the result of the divide in that case.
Correct.
Right? It's just moving some other unrelated thing.
But even if the next instruction was moving that instruction would be blocked, and the CPU would be continuing to look down the stream of instructions for something that finally didn't depend on anything that was currently being busy.
Right.
And it's amazing to think that can be done in silicon quickly. But wait, there's more. One of the problems that you hit very quickly, if you're looking for more work to do, you're looking for these dependency chains, these DAG nodes that don't relate to each other so that you can get as much parallel work being done as possible, is that very quickly you get bottlenecked on those registers, those global variables. classic, if you imagine, again, going back to 6502, you basically only had one register. It was the A register. The X and Y registers were over there as well, and they were used for indexing. But let's assume that you had something akin to only one register. And we issued that divide, right? So that divide happened, and the result's going to go into the accumulator. And then the next instruction was to say, and store that result in some memory location. And then the next instruction was, and now load a different value into the A register because I need to go and do some additions. Right. Well, at that point, I have to stop because I can't write into that accumulator register because the divide's using it right now. So we grind to a halt again. What happens as the instructions, the microoperations flow through from the decoding unit into this out of order system is that, as well as looking at the DAG of dependencies between them, it's also rewriting those registers that you gave it, and it's using tons of internal temporary register names. So in the example I just gave, that first divide, that's going to write into like A sub 0, like with a little subscript 0. But as soon as I do mov a value into A, I've completely obliterated what used to be there. I've just moved another value into it, and at that point, the CPU goes, well, that's a different A from the last A. So I last used A sub 0. Now I'm going to use A sub 1. This is a trick that compilers will do themselves, right? As compilers are looking at stuff, they'll be like, well, I can reuse this or I can not reuse that. But it's happening in silicon. So now we've got A sub 0 and A sub 1, and now suddenly they're two independent instruction flows again, and now they can be parallelized. And this is, again, parallelized within a single thread of execution on the CPU. And that's so cool, right?
Is it fair to say that this is just like another classic example of the problems to so many things in computing is another layer of indirection? It's sort of like we have these backward compatibility reasons why we can't just change all these instructions, right? But we don't want the hardware to look like this anymore, right?
Right.
So now what are we going to do? Okay, well, we'll just pretend like we're executing these instructions, and underneath the covers we can do whatever we want. And like that effect is, sort of like a classic programmer trick, right? Like I have some API that the guy before me wrote, and I hate it, but I'm stuck with it because that's what everybody uses. And so I'm going to change the implementation of it to do something different that's much faster or much more efficient or whatever, or, fits the architecture that I have or is cheaper. And that's so now assembly is just basically like an API at this point, and we're just using it to drive all these.
And as you say, it sort of has to be backwards compatible back to like 1970s era code because we're stuck with it. So that's a really interesting observation. And it's one that Intel themselves made, and they decided, well, what would it look like? And I apologize for those who probably know a lot more about this than me, but like, they decided to investigate what would it look like if we actually switched to something which was more amenable to easy execution on the CPU, but doesn't require all this trickery. And they came up with the Itanium, which was a very long instruction word chip with thousands of registers that you could actually access, or hundreds of registers that you could access. And by very long instruction word, that means that each instruction, I'm putting little air quotes here, is actually a bundle of multiple instructions that will run concurrently. As like a packet.
So they exposed, they peeled back the abstraction layer and they said, what if we just let you run what is essentially our microcode directly?
Kind of, yes, yeah, exactly. And they said, let's invest in smart compilers that can work out how to rearrange and pack the code that you've written into these instructions.
Yeah.
But it turned out to be a dead end. Either the compilers just weren't up to the task, and given how good compilers are, I suspect that's not it. Or else, what we don't get with that approach is any kind of dynamism. Right? There's a reason why I kind of use a JIT as an example, because a JIT has extra knowledge at the time. It has the dynamic environment. Like if you look at how the JRE works, and I'm switching out to analogies left, right, and center here, but like, it's very hard to statically decide whether or not something should be done one way or another. But it could be trivial to make that decision when you have dynamic information in front of you. Like, which of these two branches is more likely to be taken? I don't know.
Sure.
Is it the same way that I went the last 80 times? Yes. Well, then this is now the more optimal route to take. Whereas staring at code ahead of time, you've only got so much information. And especially when you add complexities like, I alluded to the divide taking forever. Sometimes those divides are dependent on the data that's being put into them. And so you've got a data dependency. Like, even if you're dividing two 64-bit numbers, it can take fewer cycles if the numbers are smaller or bigger, like actual magnitude of the numbers. And so there's a huge amount of dynamism that comes. Another thing that's very hard to predict is memory latency. We've got so many layers of caching now because RAM has never really kept up with the speed of the CPU. So you don't know if something's going to be in cache or out of cache. And so statically trying to predict that and kind of padding your VLIW code, it's almost, I'd say it's impossible.
Got it. So is it the case that sort of like breaking the abstraction here has then constrained what you can do underneath the abstraction, and therefore made it less efficient because now you're making promises that you're trying to make promises that may not hold up in the dynamic environment of actually running the code.
Right.
Like you're sort of implying that certain things will be fast or certain things will be slow or certain things will be more memory efficient when they're not necessarily, because it just depends. But if you've pulled back that abstraction, now the compilers in this case, which are sort of the things producing this, now sort of like can't really, they're just sort of too smart for their own good. Well, is that a reasonable way to think about it?
I think so. No, I think so.
There?
And whereas in a software JIT situation, which can also take advantage of the information, and like I said, like you can observe the pattern of code and kind of make a decision to say, well, I'm going to re-optimize this particular area of code. I don't think that even a software JIT that's producing code for, say, Itanium could observe enough information at the sort of micro level to take full advantage of this. Nowadays, the CPUs have hundreds of out of order buffers, so they can be like 200 or 300 instructions ahead of themselves. So if there's that one slow memory load that you're stuck with, as long as it can find enough enough useful work to do that can be predicted, which are a lot of ifs, but again, all these things are getting very clever, then that one slow load isn't going to block you from doing too much work. You're going to be able to tear through. And in fact, there's another sort of cunning trick that, so switching away back from this Itanium pre-compiled solution to the problem. So thinking about what a single CPU actually looks like, we've got the front end, which is this thing that's going to do the fetch, the branch prediction. It's going to fetch, it's going to decode and generate a bunch of micro operations. And then there's going to be some kind of magical renaming, which is the thing I alluded to, where it rewrites what registers you're actually using to be internal ones you can't even address. So I can't even say the name of these. They're totally internal to the CPU.
Yeah.
Then they kind of put in
the temp directory of registers.
It's exactly that. That's exactly what it is.
Yeah.
But those get all thrown into a big pot of like, here's all the instructions I would ideally like you to run. And now the out of order core is going to just pick off the ones that can be run. And then finally they get completed in order again. There's like a big master list of like, well, this is where we're good to. These things have actually happened. Anything below this mark is like may have completed out of order, but we have to make it look like it happens in order. And that's where, for example, even if it's run ahead of itself, but there was a page fault or, a seg fault on an instruction, which maybe takes a while for it to discover, the seg fault doesn't happen until the instruction that caused the seg fault retires, and then it aborts everything that's not happened after it. So that's kind of how that magical time traveling aspect happens.
Building a software emulation of this seems like years of work to me. It's just mind-blowing that there's like physical hardware that is making all these kinds of decisions. That's just incredible.
It's really it's an stunning achievement. And the most interesting thing to me is that this information is hard to come by. Intel deliberately doesn't try to tell you very much about what's going on underneath this layer because they want to have reserved the right to change it quite reasonably. Their API and contract sort of ends with you at the ISA, at the machine code level.
Right. Well, yeah, I do the same thing.
Exactly. But
don't look under the covers because I might want to change my mind later.
Exactly. But, Hiram's law, the law that, any observable side effect will be used by somebody and become relied on by somebody comes into play. But yeah, the interesting thing is all this information is inferred from some information that's in the manuals that you get from Intel, but just an awful lot of reverse engineering by a community of dedicated engineers who are using the performance counters and seeing when things tick up. How often does a front end re-steer? Intel doesn't really tell me what that particular counter is measuring, other than if it try and keep it as low as possible. But I can run my code and sort of see under what conditions that happens, and I can start building a theory. And the people like there's Travis Downs and Agner Fogg, Peter Cordes. There's a few really interesting people. I mean, like Agner Fogg, for example, he's a Danish professor of anthropology, which is like the most strange hobby to have. But I mean, who am I to throw stones in that respect? But yeah, it's really interesting that this is not as well understood, even among the people who are really, really interested in it.
I mean, are there intellectual property reasons why? I can imagine.
There are security considerations.
Yeah, that too, of course.
So just to sort of, I've mentioned about Spectre and Meltdown at the very beginning as being like the scary reason why people might think of this. Well, the sort of like the mechanism by which they attack is absolutely core to that thing I was talking about. Like, when a fault happens, it sort of erases everything that happened after the fault, but we know that several hundred instructions may have actually run based on speculating that the fault wouldn't happen, and then the fault did happen. Now, as I said, this retirement sequence happens strictly in order, so until an instruction has retired, it's as if it didn't really happen. So we can throw that away. So you're like, well, how can possibly this be a problem, right? Although we may have done some work beyond the fault, it will get thrown away. And so it's not visible to me. I can't see past it, right? That is unfortunately not true, because also in this system is the CPU data and instruction caches. Those can't be undone. Any changes that happen in them, and now I'm not talking about like data that's changed inside the caches, because it won't actually have been committed. But if somebody has read from main memory at a particular address, that will now be in the cache. That value will be in the cache. And now I can, after that fault has happened, I can go back and say, how quickly can I read this memory address? Oh, it only took 3 cycles, therefore it must be in the L1 cache. And the only reason it must be in the L1 cache is because my little targeted attack that I did over here caused the speculation system to get way ahead of itself and pull in some information that was in the cache. Now, I don't know what was in that information, but if I can contrive a situation in which the address of the read corresponds to a secret piece of information that I shouldn't otherwise have access to, I now have a way to sneak the values out by just doing timing on the cache. And this is a very big topic, and I'm really not doing it as a proper service here, but that kind of mechanism there's like the dirty secret is the undo buffer that we have inside the instructions for like, whoops, I didn't mean to do those things, can't undo the side effects of cache, things being read into the cache.
So this is like you have some data structure where the address in memory tells you something important about the data itself, like a hash or something like that, where it's like, oh, well, this value gets written to index 0, this one gets written to index 1, index 2, so forth. If you know that, I guess it's almost like a, what is that called? A Bloom filter?
There are some things. I mean, you can actually do a much more simple thing, because if you can control the code that's going to run, and so, for example, the canonical example of that is the safety mechanisms around say a JavaScript JIT engine, right? You're doing an array access, and you want to, you go out of your way to read within the bounds of the array over and over and over and over and over and over and over again. And now the branch predictor has learned that you never ever trip outside of that check that must be in the JIT somewhere that says make sure that they don't read outside of this array, right? I've made myself a 256k array, and I've sat there reading 1,000,000 times out of it. And so now the CPU is essentially, it's cold for it to deal with the exceptional case where inside the JS engine it's going to throw an exception to say out of bounds access, or it's going to return like the undefined or whatever it's going to do. But it has to do something different. Now, I happen to know that my buffer, at some giant offset from my buffer, if it were to actually try and read there, then I'd be reading some protected piece of memory that I shouldn't otherwise be able to access, right? Something outside of my sandbox. And so what I'm going to do is I'm going to read my 1,000,000 times inside arrays, and then I'm going to suddenly read out of index, and then as soon as I've got that value out, which will never actually happen, but the speculation will get that far, I will then take that value and immediately use it to read one of 256 different cache lines, and then I hope that I can do that before the branch predictor goes, "Whoops! I didn't mean to go this way," and then it all gets undone, and then I get my undefined returned, and I go, "Oh, cool!"
So you're using the value that you read out to do another read, right?
Exactly.
Which now will show up in your analysis, essentially, of like, oh, this one was really fast. So I'm going to read some value that I don't know out of memory, and let's say it's 3, but you don't know that, right? And then you're going to read whatever value you read's index into the memory, right? Yep. And that turns out to be 3, and now 3 is fast.
Exactly,
so now
right.
You know 3 is fast, and the secret value is 3.
That's right. And exactly
okay.
that. And there are different ways of achieving, and that's called a side channel attack. It's a side channel. It's like a way of exfiltrating information that isn't through sort of the architectural state of the computer.
Got it.
So we got a bit derailed there, not as much as we have any railings and any of these things. But one thing I did want to talk about was going back to that big soup of out of order execution things. So we had the front end, we decode a bunch of stuff, we get micro operations, they get thrown into this giant soup. They've been rewritten to use the internal registers, and now we're trying to use, we've got an adder, we've got a multiplier, we've got a divider, we've got multiple of these things, right? They're called execution ports. There's usually between 5 and 8 of them in different things, and they can do different things. But the sort of the goal of the out of order system is to try and fill up all these parts of the silicon with useful work to do. And as we've said, one of the ways that it can do that is to get way ahead of itself by predicting branches and starting to do loads of work that maybe is totally speculative. Another thing it can do is rewrite the registers so that more seams of independent work can be found in a single stream of instructions. But there's one more clever trick that you can do. For very little silicon cost, what if, instead of having a whole other CPU to make on the side, what if I just have another set of registers? Not even the internal rewritten ones, just the external registers. They do have to, I said at the beginning, there isn't really a box called EAX with a 1, 2, 3 in. Well, there is one canonical one. And that's in fact what that retirement stage is doing, is it's writing the real value of EAX back into the actual real EAX register somewhere, so that, anyway.
Right.
But for a small cost of having another program counter and another set of all of the registers, of which there are 16 or 32 of them, I can get another thread, and I'm putting air quotes over this. So what if I were then to say to the front end, every other cycle, read from either the first program counter or the second program counter. And when you read from the first program counter, tag it to say, these are different registers from the other program counter. So I kind of have 2 sets of front end state. So now every other cycle, I'm reading 2 completely independent streams of instructions from 2 different physical places in memory. Once they've been through the rewriter, we know that they won't be able to talk to each other. So like the stream 1's EAX is a different physical register from stream 2's EAX. But once they've been rewritten to internal register 1, 2, 3, 4 or 1, 2, 3, 5, whatever, it doesn't matter. At that point now, we've got twice as much work to do that is guaranteed to be independent because they're from 2 completely different streams of execution. But I haven't got any more adders or multipliers or dividers or anything. I just throw that into the big soup in the middle of the out-of-order execution system, and naturally we've got 2 non-overlapping DAGs that are being processed.
Right.
And provided we just have the tiny one bit that says the ultimate result of this needs to go back to EAX in hyperthread, and I'm going to call it that now, hyperthread 1 or hyperthread 2, we've got twice as many sources of independent work to do for very little cost.
So like very sort of naively here, if I had 2 programs, one of which was a very long series of adds and the other one was a very long series of subtracts, you could mix those 2 instructions together and know that they would never overlap and basically do them all in parallel, because you know that they're never going to do two adds into the same register at the same time.
Correct. Now, adds and subtracts happen to fall in the same category because they're exactly the same operation when it comes down to it. But like if you said multiply and add,
See?
Absolutely. Or, linked list,
Yes.
one's reading through memory really fast, whatever. So you get for free, inverted commas, at least a very small cost of this little extra architectural state. You get twice as much potential for filling up those 7 or 8 real work ports, these execution ports, with useful work that can allow you to make forward progress. And that's what hyperthreading was. And so that's another way of getting parallelism. We've got instruction level parallelism, which is itself the ability for the CPU to go out of order and say, well, I can run more than one instruction at a time from a single stream. Then you've got hyperthreading, which says, well, I can interleave more than one CPU's worth of instructions as long as I just do a tiny bit of accounting to make sure that they don't mix up with each other, which has led, again, to more of the kind of scary problems that you have. Like Spectrum meltdown type things. I forget which ones are specific to hyperthread siblings, but there are some. And then even just at the instructions themselves, we can use single input multiple data instructions where, you can treat a single instruction as being, well, actually, this is acting on 8 independent ints at once. But that's a whole other topic, I think, for another time. But that's another level of parallelism. And that's before we even go to genuinely multi-threading where they said, we can't make the chip go any faster, but what we can do is we can put 8 copies of the chip on a single die.
So where are we in the timeline? What year is it?
Oh, that's it.
What year is it?
What year is it? Who's the president?
Yes. Yeah. We've talked about all these technologies up to this point. What year is it?
That's a great question. So my sort of memory of where I started looking at certainly Intel CPUs was the mid-late 90s. And in fact, I was working for a company who were doing some work for Intel at the time. I remember the very first 233 megahertz Klamath got delivered which was the name of the Pentium 2, got delivered to the office. And even though I was the new guy in the office, I was tasked with getting it up and running and working, which was, painful, all these strange drivers and things that needed to be installed. And actually ultimately ended up inheriting it and taking it home, which was a whole other story. But in our lunchtime Quake sessions, I had by far the best ping. It was brilliant because no one else had a computer that was even as close. It was wonderful. It didn't make me much better at Quake, but it was a lot of fun at the time. But, that era was sort of the last era where you had any hope of really understanding, or at least getting help from Intel about like how their CPUs worked. Like I don't really actually exactly remember when, but it was at least Pentium 1 where they were told us rather explicitly there's a U pipe and a V pipe. And if your instructions look like this, they can go into the U pipe. And if they look like this, they can go into the V pipe. And then you could sort of sit down and hand arrange these pairs of instructions. So this is very much before the more complicated stuff we've been talking about. Around 2000 was when the NetBurst CPU came out. And that was one of the ones that definitely used microcode by that point. So micro operations. And rather interestingly, that took a sidestep down. We didn't talk about micro operations themselves, but the whole decoding thing is quite complicated, and so there's caches for that as well. That took an interesting sidestep down an avenue of something called trace caches, which is a sort of an alternative way of kind of encoding both the branch prediction and the decode of the stream of instructions that happened when you went to that particular place. And so it was like there was a cache that said, hey, the last time you got to address 1, 2, 3, 4 with this prediction of what branches might look like, here's just the pre-decoded micro operations. Half the work's already been done for them. Just start executing those things and only just abort if you hit the wrong one. If you discover along the way that you've made a mistake, you have to undo it and go back. And the problem with that is it just didn't work as well as the engineers thought it was going to work. So, and at this point, we're still in like 32-bit processors for what it's worth. Around this time, though, AMD were working on a 64-bit extension, and there was some kind of argy-bargy back and forth between AMD and Intel about who owned it and how they could do it. And it's about, I think 2001-ish, they came to an agreement over a patent, and I think that was like a sort of unilateral patent agreement between the two. They wouldn't go after each other for the things, and so in 2004. the first 64-bit processor came out, and it was an AMD, which was quite a coup. I mean, I imagine lots of heads rolled inside Intel when they were beaten. I think it was another couple of years before the Core processor came out, and that was 64-bit. So yeah, in the sort of those early 2000s is when like the most of the sort of micro operation stuff started to be, to my knowledge anyway, more used. You know, my real deep dive of this stuff starts in the sort of 2006 plus era of the Core, which was a separate offshoot. It was actually the original. There was a team in Israel who were doing the mobile version, the Pentium M. And when the whole trace cache that was inside the NetBurst seemed to be a dead end, they stepped up to the plate and said, hey, well, how about we take the mobile Core, take some ideas from the trace cache, but move on in a different direction. And that seemed to work out pretty well. So 2000s, 2010 was the sort of Sandy Bridge era, which had reintroduced, ironically, something called the micro-operation cache, which is different from the trace cache, but morally in the same sort of ballpark. But it didn't try to be as clever. It wasn't storing entire threads of execution like, hey, if you get to this address, then this is what you're going to do until you discover you've made a mistake, which is actually genuinely more like what a JIT does right nowadays. A JIT will kind of say, hey, this is this bit of the code. We did this last time. Let's do that. But it was more like a traditional cache where there's still logic that's sort of pumping out which instruction should be next. And it goes, well, rather than go to memory and pull down and decode the instruction, let's just see if that memory address maps to somewhere that's in our micro-operation cache. Oh, it does. Okay, that saves us going out to memory at all and doing the decode. So it's like a cache on the other side of the decode. Yes. Oh, sorry. I think I've got a note here actually. The 2003 was the AMD Opteron, which was the first 64-bit machine, and then 2004 was the Intel Nocona, which was the 64-bit bit. And it would be rude not to mention ARM processors here as well. So the ARM processors started off, as I love to say, as they were a co-processor to the BBC Micro, which was a great, fun thing. In fact, the ARM 1 was the sort of like the engineering sample for that was a coprocessor, and it printed out as "Hello, I am ARM" or something with that. And the cool little thing about that story is that they had no idea what the power consumption was going to be like. And after they realized it was booted and running, they realized they hadn't actually turned it on yet. It was running, but it was the I/O pins. There was enough parasitic power coming from the I/O pins from the device that it was plugged into that the thing just was like working. So at that point, I think they realized they were onto kind of a low power thing, which obviously has been a theme ever since for them. They're in every cell phone ever. But you know, all the levels of sophistication that have happened in Intel have happened in ARM. I haven't followed them as closely, but you know, the M1 amazing achievement and the M2 that's going to be coming soon from Apple, who have licensed the ARM ISA, but essentially have completely re-implemented it themselves with all the same kind of tricks and the same depth of pipeline and the same...
Oh, I didn't realize the M1 came from ARM's legacy. That's interesting.
Right, yeah. Well, these are all... I mean, they have to pay ARM for the ISA to license essentially the encoding of the instructions is what they're paying for, I believe, and like the idea of it. Otherwise, you know, I'm sure they would have preferred to do everything themselves, but it's only so far you can go. But yeah, it's and the other thing about the M series is that they've gone for both a big and a small core. So they've actually gone from heterogeneous cores. So at the moment, like any Intel CPU, if you've got 8 CPUs, they're all exactly the same. But in an M1, you've got the Firestorm core, which I think is the big one, and the Ice Storm core, which is like a small one, and there's like 4 of each. And so there's some clever power management stuff that the operating system can do to say, well, let's just put these lower priority things on the lower power consumption CPU that isn't as fast, whereas this graphics editing code or whatever can run on the other one. And I'm super vague on this, but I just know that it exists, and it's coming, I think, to everywhere. So yeah, there's an awful lot of things that go on inside that little chip, and you know, we haven't even talked about how the caches work, how the branch predictor works. I often joke that if we were to somehow come up with a way of getting the previous year's worth of lottery numbers encoded as a sequence of jumps, we could probably use the branch predictor to predict the next set, and then I can retire, because they are so good. They are just so clever, and the levels of which the engineers go to, and obviously this is into trade secret area. So reverse engineering those branch predictors is challenging. And even just getting the idea. So that the pipelines now are so big and weighty that the old school idea about what a branch predictor is like, is this branch taken or is this not taken? That's kind of how I've described it. But really, even the is it a branch, right? I've just pulled out 16 bytes of memory, and certainly for an Intel, is there a branch in there, and does it have a destination, like an unconditional branch, a jump? If I have to wait 5 or 6 cycles for it to get down all the various pre-decode steps and all those bits and pieces before it gets to the actual decoder, it goes, oh, sugar, there's a jump, an unconditional jump to 100 here. Then I have to re-steer all the 4 or 5 steps beforehand. So there's a predictor for the destination of a branch, or even if there exists a branch in just an arbitrary block of code. And so before anything happens at all, there's this sort of magic 8 ball that the BPU shakes, and it goes, there will be a branch in the next fetch. It goes, brilliant. Okay, well, the next one we're not going to get from where we think it's going to come from. We're going to get from like 100. Off we go. It's just so clever. So clever. And so much of this stuff that we take for granted. We just write code and it runs, and largely we can ignore it, which is a testament to where we are. But I have a cool little example where you can demonstrate the effects of the branch predictor even in Python, right? You can write a relatively straightforward piece of code that runs, I'm not going to say a lot faster, but reliably measurably faster one way than another. And they're identical workloads. It's just whether or not the branch is predictable that's in the heart of it. And that's like 10 layers deep inside the Python interpreter, for heck's sake. So It does affect us all. It's just interesting to know about, and very rarely does it actually make a difference, but it's cool to know that it's there.
Well, I feel like I've learned a lot today.
It's been fun, and I mean, if people are interested in hearing more of this stuff, we can dig into something else along this line another time, or...
This is. There's like 2 or 3 other podcasts that I'm sure are going to come out of this. And this is really good stuff.
I'd like to shout out as well. There's a friend of mine's podcast who he and a friend are doing far, far deeper and far more authoritative podcasts on these kinds of subjects. So if you're interested in this stuff, I would heartily recommend going to TLB Hit, which is tlbh.it, and subscribing to JF Bastien's and I forget his co-host's name, but their podcast is brilliant. But ours is also going to cover some of these topics, hopefully, maybe just in a different way and to a different kind of audience.
Well, you're definitely getting the layman's perspective on some of these things. So hopefully, I'm doing that Larry King thing where I ask the questions that people are wondering in their heads. But I don't know. We'll see.
Fantastic. Well, I guess until next time.
Until next time.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbold. Find the show transcript and notes at twoscomplement.org. Contact us on Twitter at 2CP, that's at TWOSCP. Theme music by Inverse Phase, inversephase.com.